Every breakthrough in modern artificial intelligence, from GPT and Gemini to Claude, DeepSeek, Quinn, and Llama depends on one piece of hardware more than any other, the graphics processing unit or GPU. Without GPUs, training today's large language models will take years instead of weeks. Some models will simply be impossible to build. But here's what makes this interesting. GPUs were never designed for artificial intelligence. They were invented to render video games. So how did hardware built for drawing pixels become the engine behind the AI revolution? In this video, we answer that question. We will cover where GPUs came from, how they differ architecturally from CPUs, why transformer operations map so naturally onto GPU hardware, what TFLOPS actually measures, and why memory bandwidth often matters more, how to calculate exactly how much GPU memory a model needs, and how quantization change who can run AI. By the end, GPU specification will stop feeling like marketing numbers and start making intuitive sense. Let's look at the origin of the GPU. To understand why GPUs exist, you need to appreciate the problem that created them. Let's go back to the 1990s. At that time, computers were beginning to run increasingly complex 3D games. And those games suddenly needed to draw thousands of triangles, millions of pixels, lighting, shadows, and texture, all within a single frame at 30 to 60 frames per second. That's a new frame every 16 to 33 milliseconds. The CPU couldn't keep up, not because it was slow, but because it was solving the wrong problem. A CPU is built to handle almost anything you throw at it: running an operating system, executing a database query, compiling code, and browsing the web. To handle that variety efficiently, GPUs develop sophisticated capabilities. They predict which code path you're about to take, reorder instructions to avoid idle time, and maintain large cache to keep frequently used data close. All of that makes a CPU extremely capable at sequential, complex, unpredictable work. But rendering a frame doesn't need any of that sophistication. The color of one pixel has no bearing on the color of another. Millions of pixels can be computed entirely independently. What graphics needed wasn't a smarter processor. It needed thousands of simpler processors running simultaneously. This insight led to the GPU. Instead of a handful of powerful cores handling tasks one after another, a GPU uses thousands of simpler cores all doing the same operation on different pieces of data at the same time. This is called data parallelism, and graphics workload are nearly perfect examples of it. Now let's look at the unexpected connection to AI. Fast forward to the mid-2000s, and researchers working on neural networks noticed something striking. At their core, neural networks are mathematical systems. Every prediction they make traces back to one operation repeated across billions of parameters. Y equals to x multiplied by w plus b, where x is an input, w is a matrix of length, weight, and b is bias. This same operation appears in every layer, every attention projection, every feed-forward layer, and every output edge. Training a large model means running the computation across billions of examples and thousands of update steps. That's trillions of multiply and add operations, all of them independent, all of them parallelizable, exactly like pixels. The hardware built for games turned out to be nearly perfect for deep learning. NVIDIA recognized this and in 2007 released CUDA, a programming framework that let researchers write general-purpose code for GPU hardware without touching graphics APIs. This decision, more than any other breakthrough, is what ignited the deep learning revolution. Let's look at the difference between CPU and GPU. People often assume GPUs are just faster CPUs. They are not. The difference goes deeper than speed. Think about it this way. A CPU is a Michelin star chef, one person, extraordinarily skilled, can prepare any dish, handle any special request, improvise when something goes wrong. You wouldn't trade this chef for anything if your dinner party has a complex, unpredictable menu. A GPU is a factory with thousands of workers, each doing one specific job on a conveyor belt. Individually, they are less impressive. But if your job is producing a million identical bottles per day, the factory wins by an enormous margin. Although both CPUs and GPUs perform computation, they are optimized for different objectives. A CPU is engineered to minimize the time it takes to complete a single task, a property known as low latency. A GPU is engineered to maximize how much work gets done per second by executing thousands of operations in parallel, a property known as high throughput. These two goals pull in architecturally opposite directions, and most of the physical design difference between CPUs and GPUs follow directly from that. A modern server CPU dedicates roughly a third of its silicon to cache memory and another third to control logic that helps it handle complex, unpredictable programs efficiently. The GPU redirects most of that area into raw arithmetic units. The consequence is significant. An H100 GPU has over 16,000 cores and 528 specialized matrix multiply units called tensor cores. Each individual core is far simpler than a CPU core. But when your workload is the same arithmetic operation repeated billions of times, as in training a neural network, that army of simple core is far more powerful than a handful of sophisticated ones. Let's look at why transformers love GPUs. To see why GPUs are so well suited to modern AI, let's look at what actually happens when you send a message to an LLM. The model doesn't process words, it processes numbers. Your input is tokenized into integer indices, converted into vectors, and then passed through dozens of layers of computation. The most expensive part of each layer is the attention mechanism. In self-attention, every token in the input sequence is transformed into three vectors: a query Q, a key K, and a value V. These vectors are then used to determine how much attention each token should pay to every other token in the sequence. Mathematically, this is expressed as attention QKV equals to softmax of Q multiplied by K transpose divided by square root of D subscript K, or multiplied by V. The first major computation is the matrix multiplication Q multiplied by K transpose. This operation compares the query vector of every token with the key vector of every other token, producing a similarity score for each pair. If the sequence contains n tokens, the result is an n by n attention matrix containing n raised to power 2 similarity scores. For example, with an 8,000 token sequence, a single attention head computes 64 million similarity scores. Although this sounds computationally overwhelming, each score is independent of the other. That independence allows a GPU to distribute the work across thousands of processing cores, computing millions of comparisons simultaneously instead of one after another. The same pattern repeats throughout the architecture: feed-forward layer, output projection, and the embedding lookups all reduced to matrix multiplication, and matrix multiplication is the exact operation GPU tensor cores were designed to accelerate. This is not a coincidence engineers worked around, it's a fundamental structural alignment between the mathematical form of deep learning and physical design of GPU hardware. Now, let's look at what TFLOPS actually means. The H100, for instance, is rated at 3.9 petaflops of FP16 tensor core performance. Let's understand what that actually tells you. A flop is one floating point arithmetic operation, such as addition, a multiplication, or a fused multiplier which computes A multiplied by B plus C in a single step. T-flop means 1 trillion such operations per second. Petaflop means 1 quadrillion such operations per second. The H100 is rated at 3.9 petaflop. It's saying under ideal condition, this chip can execute 3.9 times 10 raised to power 15 arithmetic operations per every second. That's a remarkable number. There's one important catch. T-flop mirrors a GPU's theoretical peak performance. It assumes every compute unit is busy every clock cycle, and that data is always available exactly when it is needed. In reality, that almost never happens. Real applications spend time waiting for data, synchronizing work, or executing operations that don't fully utilize the hardware. As a result, the performance you observe is often much lower than the number printed on the specification sheet. That's why TFLOPS tells only part of the story. A GPU can have enormous computational power, but if it cannot move data quickly enough, much of that compute capability sits idle. This brings us to another specification that's just as important as compute performance: memory bandwidth. And for many AI workloads, memory bandwidth, not raw compute, is the real bottleneck. We've talked about computational performance, but there's another specification that's just as important for AI: memory bandwidth. To understand why, let's look at what happens when a large language model generates text. Before the GPU can perform a single matrix multiplication, it first has to load the model's weight for memory into its compute unit. For modern LLMs, we are not talking about a few megabytes of data. We are talking about billions of parameters. A 70 billion parameter model stored in FP16 requires roughly 140 gigabytes just for the weight, and those weights must be read from memory over and over again as the model generates each new token. The speed at which data can be delivered is called memory bandwidth. It measures the maximum amount of data that can be transferred between memory and the processor every second. It is typically expressed in gigabytes or terabytes per second. NVIDIA's H100 GPU, for instance, can transfer approximately 3.35 terabytes of data every second. That sounds enormous, but when you are working with models containing tens or hundreds of billions of parameters, that bandwidth gets consumed remarkably quickly. At this point, it is helpful to distinguish between bandwidth and latency, two terms that are often confused but describe different aspects of memory performance. Bandwidth answers the question: how much data can be transferred every second? Latency answers a different question: how long does it take before the first byte of data begins to arrive? Imagine filling a swimming pool. A garden hose starts delivering water almost immediately, but only a small amount flows each second. A large industrial pipe may begin flowing after a similar delay, but once it does, it delivers vastly more water every second. Both systems might have similar latency. The difference is the bandwidth. For AI workloads, bandwidth is often the more critical limitation because the GPU must continuously stream enormous amount of model data into its compute units. GPUs manage latency by keeping many operations in flight at once. once. When one group of thread is waiting on a memory request, the GPU scheduler immediately switches to another group that is ready to compute. This ensures the chip stays productive while waiting for data to arrive. This leads to an important insight about how LLMs actually run. A GPU might be capable of performing hundreds of trillions of mathematical operations every second, but if it spends most of its time waiting for model weights to arrive from memory, those powerful compute units remain underutilized. This becomes especially clear when you compare the two phases of LLM inference. When processing your input prompt in what is called the prefill phase, the GPU handles a large batch of tokens at once and performs large matrix multiplications. There is plenty of arithmetic per byte of data loaded, so the compute units stay busy. This phase is compute point. When generating the response one token at a time in what is called the decode phase, the GPU processes a single token per step. The matrix multiplications shrink dramatically, and the GPU ends up loading billions of weights from memory while doing relatively little arithmetic per byte. The bottleneck shifts entirely to memory bandwidth. This phase is memory bound. That's why a GPU is only as effective as its ability to keep its processor supply with data, and why modern AI GPUs don't just become more powerful with each generation, but also dramatically increase memory bandwidth. For many large language models, memory bandwidth, not raw compute, is the factor that ultimately determines how fast tests can be generated. Now, let's look at how much GPU memory an LLM needs. One of the most useful things you can do as an AI engineer is to estimate whether a model will fit into your GPU's memory. Fortunately, the calculation is surprisingly simple. Every parameter in a neural network is stored as a numerical value. The amount of memory required depends on two things: the number of parameters and how many bytes are used to store each parameter. This gives us a simple equation. Memory equals to number of parameters multiplied by bytes per parameter. But what exactly do we mean by bytes per parameter? Computers store data using bits, where a single bit can represent only a 0 or a 1. 8 bits make 1 byte, which is the basic unit used to measure memory. Different numerical formats use different number of bits to store each parameter. FP32 uses 32 bits per parameter. FP16 and BF16 uses 16 bits. Int8 uses 8 bits. Int4 uses 4 bits. Since 8 bits equals to 1 byte, converting from bits to bytes is straightforward. FP32 will store using 4 bytes. FP16 and BF16 will use 2 bytes. Int8 will use 1 byte. And Int4 will use 0.5 bytes. Let's apply that to a 7 billion parameter. If every parameter is stored using FP32, each one occupies 4 bytes. That means 7 times 10 raised to the power 9 times 4, which is 28 times 10 raised to the power 9 bytes. Since 1 gigabyte is approximately 1 billion bytes, that's roughly 28 gigabytes of memory just to store the model's weight. For other formats, BF16 and FP16 stores the same model using 14 gigabytes. Int8 stores the model using 7 gigabytes. Int4 stores the model using 3.5 gigabytes. At this point, you might notice something surprising. The model still has exactly the same number of parameters. We haven't removed any of them. We have simply changed how these numbers are represented in memory. This figure represents only the model's weight. Running an LLM also requires additional memory for temporary computations, cached attention states, and other runtime data. But even this simple calculation gives you a remarkable good first estimate of the GPU memory you will need. And it raises a question you are probably already asking. How can the same 7 billion parameter model require 28 gigabytes in one format but only 3.5 gigabytes in another? That's exactly what the next chapter is about. Let's look at quantization. Quantization is a process of representing the model's numerical values using fewer bits. Instead of storing every parameter as a 32-bit floating point number, you store it using 16 bits, 8 bits, or 4 bits. Fewer bits means less memory. Less memory means lower bandwidth requirement, and lower bandwidth often translates into faster inference. To understand how this works, we need to look briefly at how numbers are represented inside a computer. A floating point number is divided into 3 parts: a sign bit, which indicates whether the number is positive or negative, an exponent, which determines its numerical range, and the mantissa, also called the significand, which determines its precision. By reducing the number of bits used to store these fields, we make each parameter occupy less memory. The trade-off is that the numbers become less precise. Here's how the common formats compare. FP32 is the full precision and the training baseline. BF16 preserves the same exponent width as FP32, which means it can represent the same range of values. It sacrifices on mantissa precision, but that loss is negligible for inference and makes it the preferred format for training stability. FP16 uses a slightly narrower exponent range. This can occasionally cause numerical overflow during training without careful handling, but it works well for inference and is widely supported across GPU hardware. FP8 is a newer format used in NVIDIA's H100 transformer engine. It pushes precision further but allows the hardware to perform matrix multiplication at even higher throughput. Int 8 represent values as integers rather than floating point numbers. Because there is no exponent or mantissa, a calibration step is required to determine the appropriate scale factor for mapping floating point weighting to the integer range. When done carefully, Int 8 preserves most of the model's original quality. Int 4 is the most aggressive format in common use. With only 16 possible values per parameter, significant care is needed to minimize quality loss, and specialized techniques have developed to make it practical for large models. The quality trade-off across this format is real but manageable. BF16 is nearly indistinguishable from FP32 for inference. Int 8 with careful calibration preserves most of a model's performance. Int 4 introduces some degradation, but for models above 7 billion parameters, the weight matrix tends to carry enough redundancy that the loss remains acceptable for most applications. The practical impact is significant. A 70 billion model that requires 140 GB in BF16 fits in roughly 35 GB at Int 4, which is the difference between needing multiple high-end server GPUs and running comfortably on a single well-equipped workstation. Without quantization, most of today's open source models will be inaccessible to anyone without data center hardware. In conclusion, when GPUs were first introduced, their purpose was simply to render graphics faster. No one imagined that the same hardware will one day power language models capable of writing essay, generating code, translating language, and assisting scientific research. GPUs didn't become the foundation for AI simply because they are faster than CPUs. They became indispensable because of their architecture, which is almost perfectly matched to the mathematics of deep learning. Neural networks spend most of their time performing the same kind of operation over and over again: matrix multiplication, vector operation, and other forms of linear algebra. These are precisely the kind of workload GPUs were designed to execute efficiently and in parallel. In this video, we have seen how GPUs evolved from graphics accelerator into the computational engine behind modern AI. We've explored how they differ from CPUs, why parallelism matters, what TFLOPS, bandwidth, and latency really mean, how to estimate the memory requirement of large language model, and why quantization has become essential for running today's models efficiently. But we have only looked at the GPU from the outside. In the next video, we will open it up and explore what actually happens inside the chip. We will dive into streaming multiprocessor, CUDA cores, tensor cores, the GPU memory architecture, and the CUDA programming model to understand how billions of matrix operations are executed every second. Thanks for watching. See you in the next video.